kind of a pain in the neck about following directions, okay? Whether, so let's try to follow directions, okay? All right, so are there any questions on doing the statically indeterminate problems? So I posted a fair amount of material. I won't do, I'll try to do one or two as we move forward in the review using the assumed force method. But again, you can do either method as well. But I posted the like lecture materials for doing assumed force method on Blackboard. Some solved problems both by hand and also by MathCAD. So when I talk about sort of flipped content, that's what I mean, right? I won't, as we move forward in some of the other materials, I will not go through all the derivations in class because some of them it's just a bit much, but you are responsible for them either through the book or through the videos that I post. Okay, so make sure you look at those when they're noted either in Blackboard on the chronological thing of how it's ordered on the homepage or in the lecture plan. Okay. All right, but no questions on the statically indeterminate problems. Okay. All right, well, if not, then let me get started with what I want to cover today. So today, like I said, I want to do two topics. They're not terribly hard, but they are kind of important. So I do want to kind of kill both of them today. So the first one is going to be thermal stresses. And then the second topic is going to be stress concentration factors, okay, which will probably set us up to our next project, okay? All right, let me make this go presentation mode. Can you see, sometimes when I do presentation mode, it doesn't broadcast. Can you see the PowerPoint slides?
Yes, sir.
Okay. All right. So section 4.6 deals with thermal stresses. This is rather straightforward concept. You've probably actually seen this in like physics 1 or something already, or if not, unfortunately, some people may have seen it over last week's freeze, right? As we have temperature changes on materials, whether they're metals or fluids or even gases, ideal gas law, with temperature change, there is an associated expansion, okay? That expansion, if it's not allowed to freely expand, if it's constrained, that's going to result in stresses occurring and possibly failure. And there are lots of applications where the thermal stresses really can become significant, okay? So there's a lot of ways to think of this. I think the most important equation that we kind of have to internalize is that the thermal strain, the strain due to the thermal expansion, is equal to this parameter alpha times the change in temperature. And alpha is the thermal expansion coefficient. Okay, thermal expansion coefficient. It's if you look at the units, strain is dimensionless. So that means that, and delta T is obviously in units of temperature, degrees Fahrenheit, degrees Celsius. So alpha will have units of 1 over degrees Fahrenheit or 1 over degrees Celsius, right? Okay. So that tells you that, if you have a temperature change, what is the thermal strain that develops in that, okay? And I'm making a point to call this thermal strain, and you'll see why in a second, right? So if you know what the thermal strain is, right, you can also figure out the elongation, the change in length. So remember, the change in length is equal to the strain times the original length. So putting in here for the thermal strain, you can get that the change in length is the thermal expansion coefficient, alpha, times the temperature change times the original length, okay? And so that's basically the governing physics equations right there, right? Now, I do want to talk about this. This is a little bit different than the way the book approaches it. This is actually a bit of a more high-level way of thinking about these thermal stress problems. And it's pretty powerful, okay? So we talked about strain as being the change in length over the original length, or for shear strain, right? This was the angular distortion, right? So for now, we're just going to talk about the normal strain, because shear strain really doesn't happen from thermal expansion, except if you have highly anisotropic materials. Okay, so that's, that's the measured strain. That's the strain we actually see, the change in length over the original length. That's actually composed of two parts. A strain that results in the mechanical stress, we're going to call that epsilon mechanical, and also the strain that results from the free thermal expansion, okay? And so if we think of this additive decomposition of the measured strain, then actually it makes a lot of these problems really easy. So the actual measured strain, what you would see by if you could measure with a ruler, or probably more likely a strain gauge, is the mechanical strain plus the thermal strain. Now, it's only the mechanical strain that gives you the stress. And so now you might say, well, that makes no sense, because you just told me, you can get thermal stresses that are pretty significant. Well, that's only when it's constrained. So let's do a little bit of a thought experiment. Okay, so I'll do something next slide. All right. So now we're going to consider unconstrained thermal expansion, free thermal expansion. So we have a bar. Okay, so this is it at room temperature, let's say, and now we're going to heat it up. So now the bar just freely expands. Okay. So in this case, the thermal strain is going to be that alpha delta T, okay? Now, because it's allowed to freely expand, the measured strain is actually equal to that thermal strain. They're equal. And then if you look at this decomposition here, then that means that the mechanical strain has to equal 0, right? It's allowed to freely expand, okay? So maybe I'll probably have this, oops. All right, so that means that actually in this case, there is no stress, because the mechanical strain is equal to 0, right? The measured strain equals the thermal strain. So that makes kind of sense. And so if you just heat up a straight bar or something like that, you will not see any thermal strain, okay? And there will be no thermal stress. Now, this is going to change when we constrain it. So now we have basically the same bar. I'm going to apply a temperature on it, but it's fixed at the ends, right? So it can't expand, all right? So we heat it up, it wants to expand, but in fact, it's constrained, so it cannot expand. And so in this case, you can't see any expansion, right? So in this particular case, the measured strain is actually 0. You can't see any change in the specimen. It's because it's constrained by those walls. So E measured equals 0. Now we do know that the thermal strain is alpha delta T. So if we look at that in this context, right, then if the measured strain is now 0, this is going to tell us that the mechanical strain is equal to the negative of the thermal strain. All right. And so if that's the case, if the mechanical strain is equal to the negative of the thermal strain, that's going to tell us that this is minus alpha delta T. So that makes sense, right? We get the negative sign because, in fact, you can think of this as two steps. We allow it to freely expand, and then we have to compress it back down. So in this case, we will get a stress, and that stress is going to be a compressive stress minus E times the mechanical strain, right? Which is minus E alpha delta T. So you get a compressive stress in here because it's constrained. So the measured strain has to go to 0. So that means the mechanical strain has to balance out the thermal strain. Okay. All right. Any questions on that? So there it is. I guess that was my second picture on that. All right.
Professor, so if it's not constrained, there's no thermal?
Okay. If it's not constrained, let's go back to the previous slide. I can. Can I go back to the previous slide? Right. So here we have free thermal expansion. In that case, it's free to expand. You do have a thermal strain. It's alpha delta T. And that is exactly what you see it expand by. It freely expands. So that is the measured strain. They're equal, okay?
Oh, okay. Okay.
And in that case, that means that the mechanical strain has to be 0. So if the mechanical strain is 0, then there's the stress is 0, right? Because only the mechanical strain gives you the stress, right?
Yes. Okay, I get it. Thank you.
Whereas down here, when it's constrained, right here, it's different. There is no measured strain. And the only way that can be is if the mechanical strain is the negative of the thermal strain, right? And so that's why you get, even though you heat it up and it wants to expand, the actual stress is a compressive stress, okay? So yeah.
Okay, thank you.
So it's a little overkill for a lot of the problems that we do in this class, but when they get a little bit more, how do I say, nuanced, a little more complicated, and sometimes it helps to kind of remember that, okay? All right, so let's look at this problem here. And so here we have a rod that consists of 2 pieces of material. AB is brass, so this is brass, and BC is aluminum, okay? So I put over here the thermal expansion coefficients and Young's modulus for brass and aluminum, respectively. All right. So this is in imperial units, so you can see I'm using 1/F as the units for alpha. You can see it's very small, right? And this is pretty typical. Alpha is going to be like 10 to the -6. That you need a really big temperature change to get a really large strain. But again, remember, very small strains still result in pretty large stresses. So that's why we have the -6. All right. Now it's fixed at the 2 ends, A and C. And what it wants us to do is it wants us to find the average normal stress in each element. And then also it wants us to find out how much this collar, point B, is displaced, okay? So it gives me the cross-sectional area, gives me the materials, and then it also gives me the initial temperature, T1, there's no stress, and then the final T. So the temperature change in this case is 120 F minus 50 F, and so that is 70 degrees Fahrenheit. That's the temperature change, okay? All right. So how can we go about solving this problem? Well, since they're dissimilar materials, or if they were different diameters, right? We have a little bit of a problem. We have to treat this as one sort of specimen. So if you were to look at this, we know physically what's going to happen, right? We're going to heat up both the brass and the aluminum. They're going to expand or want to expand a certain amount, but then we have to compress it down using compressive forces at A and C to get the change in length back down to 0. So that's going to give us that mechanical strain, right? So we need to find the compressive forces here. I'll call them P, right? That are going to make the actual change in length, the measured change in length, equal to 0. And the measured change in length is going to be equal to the change in length, due to the mechanical stresses plus the change in length due to the temperatures, okay? The thermal stuff, right? All right. Okay. So in this particular case, this is going to go to 0. So we have to compress it down by exactly what the free thermal expansion would be. So let's figure that out first, right? So if we're going to do the free thermal expansion, or, from L, right? So this one is going to expand by alpha for the brass, alpha for brass times delta T, right? And we want to get the change in length. So this is the strain. We're going to multiply that by the length, and that length is length AB. So that's how much the brass section wants to expand. Okay, we're going to add on to that how much the aluminum section wants to expand. So that's alpha for the aluminum times the temperature change. Temperature change is the same for both, times the length BC. And so that's going to give me the thermal expansion, the free expansion if it weren't constrained, right? So we can figure that number out. We know all those things, right? And so if we put into here, we can take the delta T out of everything, right? So that's going to be 70 degrees F times alpha for the brass is here, 10 to the minus 6. Times its length, which is 3 feet, or that's 36 inches, right? Plus alpha for the aluminum, which is 13 e to the minus 6. And those are units of 1 over F. I should put that in here. 1 over F times its length, which is 24 inches. All right. And now we can calculate that the total change in length is actually going to be 0.047 inches. So not too much, 47 thousandths of an inch. That's basically like less than a 16th of an inch. It's sort of the thickness of a business card type of thing. But that can still lead to a considerable amount of strain. Okay, a considerable amount of stress. All right. Now, of course, it can't expand that much. That's the free expansion. So that means that the mechanical elongation actually has to be the negative of that. All right. And so let's figure out what that would be. Both sections are going to see the same, if we do the free body diagram here, right? We have a constant internal force here of P. That's the compressive force, right? Okay, so So the elongation or the compression of the brass section, right? Remember, it's going to be P L over AE, right? And in this case, L is the length AB, and E, right? E is going to be the E of brass, okay? So this is the, if you put a compressive force of P on the brass section, that's how much it'll change length, okay? And then we're going to add on to that how much the change in length in the aluminum would be. So the aluminum will see the same compressive force P, but it has a different length. It's BC. And there, we're going to divide by A. It's the same cross-sectional area. And here we're going to use the E of aluminum, right? So this is the change in length of the brass. Well, maybe I should let's be consistent, right? That's the change in length due to the brass plus the change in length due to the, in the aluminum section, okay? And that is the total length change, mechanical length change, all right? So that's the minus 0.047 inches. That's how much it has to compress by. Now, P is the same for both, and the area is the same for both, so I can pull that out. So that's P over A, all right? And so now we got length AB over Young's modulus for the brass plus length of section BC over Young's modulus for the aluminum. And that has to equal minus 0.047 inches, okay? Well, if you look at this, here's force over area. So we could actually calculate force and then figure out the stress, but this actually is the stress. And so we have the same compressive force in the brass and the aluminum, and we have the same cross-sectional area. So the stress is going to be the same, okay? So we can solve directly for the stress. So the stress is going to be equal to the minus 0.047 inches divided by, this term here, right? And so that term there would be length of AB is going to be 36 inches over Young's modulus for the brass, which is 15 megapascals. Okay, plus the length of the aluminum section, which is 24 inches over its Young's modulus, which is 10 psi. Okay, and if you do that, you get a stress of minus 9.8 KSI. All right. So that's the stress in both the brass and the aluminum sections. Okay. It's equal. Now, if you wanted to figure out how much it actually point B moves, well, then in that particular case, right, the cross, they give you the cross-sectional area, right? So you can figure out actually the force P, right? Because the force is going to be the stress times the cross-sectional area. That would be actually, let's see what it is. So I get a compressive stress of that P is equal to minus 17.2 kips. Okay, that's the force. And then from that force, you could figure out the elongation of either the brass section or the aluminum section, and that'll tell you how much point B moves, okay? Okay. In that particular case, you know, there will actually be a measured deformation at that point, okay? And that's because, you know, the even though the stress is the same, the strains are different, right? The mechanical strains are different, okay? Are there any questions on that? I don't like solving these on the slides because I never have enough space, but. All right, so there's a couple different forms of these, but usually there's something along these lines. Like I said, there's no real strain sort of equivalent to that, and that's basically how that goes. Okay, sometimes you'll see problems where they give you like a gap to the wall, and there, in that particular case, I'm going to erase all this stuff, right? Let's erase this. Oops. I'm sure you way to clear this. Maybe if I do it this way. Can I delete that? No. I never know how to. It's always hard doing these things on PowerPoint. I don't want to erase it all. I'm just erase it enough that I can have some space here. All right. So they might give you one where there's an initial gap here, right? Delta. So in that case, remember, we're going to have the change in length, the measured change in length equals the change in length from the mechanical, right? The part that gives you the stresses, plus the change in length due to the free thermal expansion. So in that particular case, what you're going to have is the measured change in length is going to equal that gap, right? Because it's going to change, it's going to elongate until it hits the wall, and then it won't elongate anymore. So instead of the measured change in length of being 0, in this particular case, if there's a gap, the measured change in length is going to be that gap, delta. Then you can go and figure out the change in length due to the free thermal expansion, right? This is going to be alpha delta T times the length, or if it's a problem like this where there's several sections, you sum that up for each section, right? And then that will tell you how much the mechanical change in length will be, right? So that is, again, that's the change in length that you have to compress it down that gives you the stress, right? That would be free expands by alpha delta T, and then you have to squash it down, not quite that alpha delta T, because it was allowed to freely expand by delta, and then that's what gives you the stresses in the actual elements themselves, okay? And that's basically those are the two types of problems you have. Like I said, there's no shear equivalent to thermal expansion unless you have some funky, unbalanced composites or something like that, right? Okay. But again, it's a pretty important source of stress. All right. All right. The second bit that I want to talk about today is this idea of stress concentrations. And we've been able to, in this chapter, to invoke basically like Solnit-Vidal's principle, and then away from the points where the loads are applied or the component is fixed, we have a pretty good approximation of the normal stress in those regions, right? It's just force over area, and it's fairly uniform, right? Kind of like what you would see here, right? But in reality, when we have certain types of features, like these stress concentrations are an example of those, for example, like if you put a hole in the middle of the bar, you actually are going to see a stress distribution that deviates pretty significantly from that uniformed average. It looks something like that. The stresses will actually be higher at noon and 6 o'clock on the hole. And you may have noticed this in that finite element project where you applied the bearing stresses, you had higher stresses in the same orientation on that bracket. And another type of stress concentration factor was where the tapered section met the base plate. And because you have a sharp corner there, you had another stress concentration and the stresses dropped up significantly. So, obviously one way you can handle this is to do the finite elements and see what those stresses are. But historically, that wasn't always an option. There is a pretty quick way to solve those, and that's with this idea of stress concentration factors, okay? So we're going to talk about what is a stress concentration factor and how we can use that. All right, so if we look at this equation here, all right, at the bottom, this is really it, okay? So if we didn't know anything about stress concentrations and we just wanted to naively compute the stress, you would actually get this average stress, right? Where the average stress is equal to N over the area. And the area would be this reduced area here, right? So you would get a stress there, and that would be kind of this average stress, all right? Now, as I had just stated, the actual stress distribution is quite a bit different than that. And right around the hole, you see a peak stress that's greater than that average stress, right? The stress is higher. That's the stress concentration. So instead of using or reporting the average stress, we multiply the average stress with this factor, the stress concentration factor. So a lot of times it's called SCF, the stress concentration factor, K, which is greater than 1. And that gives you the peak stress. Okay, now that's the stress you want to design to. So if the peak stress is above the allowable stress, then your design is going to fail, right? At least theoretically, it's going to fail, right? So doing these stress concentration factors, doing these stress concentration calculations, we already know how to compute the average stress. So now the question is, how do I get these stress concentration factors? Well, it turns out that actually a lot of these things have been tabulated, okay? So the book gives 2 cases, and then I also, well, I don't know if I'll post online on Blackboard a compendium, a PDF with a lot more stress concentration factors for you to use if you want to in the future. But here you go. So here is the what we had in the example on this slide, right? So we have a bar under tension, and there is a hole in the middle of it, okay? So that's what's shown here, okay? Now, on the y-axis of this plot, we have the stress concentration factor, K. And it's a function of what's shown on the x-axis. So on the x-axis, we have this parameter 2R over W. So 2R is, that's the diameter of the hole. So the stress concentration factor depends upon the ratio of the diameter of the hole over the total height, W, of the bar, okay? And so depending upon what that is, you can go to this plot and you can find K. So let's pick some numbers. Let's say in this particular case, let's say we have this dimension here equal to 2 inches, and the diameter of the hole equal to not 0.08, but 0.8 inches. All right. So the radius is 0.4 inches, right? I probably should have, I don't know why I don't have inches here. I should have inches. Okay, so we want to compute this factor 2r over w, or the diameter over w. It turns out to be 0.04. So we go on the x-axis to 0.04, see where that hits the curve, and that's going to tell me that for that particular geometry, the stress concentration factor is 2.2. All right. So the peak stress that's going to occur here and here is 2.2 times the average stress, right? So we compute the average stress. So I didn't know. So let's say that the force applied N is 1,000 pounds. Okay. And, you know, they give you the equation here to compute the average stress, but it's pretty obvious what it is. It's the force, the internal force, N over the reduced area. So the reduced area is the cross-sectional area minus the hole. So it's W minus 2R, right, which is this height and this height, times the thickness, which is this dimension, okay? And so W is 2 inches, 2R is 0.8 inches, and then the thickness, I don't know why I dropped the units again, is 0.05 inches, right? So that tells you that the average stress is 1.7 KSI, but the peak stress, you know, that would be the stress you would see, you know, sort of up here somewhere. But the peak stress is going to be the stress concentration factor times that, 2.2 times that. So the actual peak stress you see here is 3.7 KSI. So it's quite a bit larger, okay? So if you wanted to reduce that stress, right, the only way you could, you know, you want to make the stress concentration factor lower. And so that means you want to be down here on the curve. So to do that, right, you want to have a larger ratio of the diameter over W, okay? So that's kind of how you go about doing those, all right? Now, you can also, another case that the book shows is the stress concentration factor that comes about from having this fillet here, right? So this sort of feature is called a fillet, okay? Not a fillet, but a fillet, all right? And that actually produces a stress concentration. So right in this area, right? You're gonna get stress concentrations right here, okay? So here's your average stress, and then you get a peak stress right at this region and this region. So same concept, right? You're still going to use the peak stress, the max stress is equal to the average stress times that stress concentration factor. So this plot here is the plot that gives you the stress concentration factor for the stepped bar with a fillet of radius r, okay? So in this particular case, we have a family of curves. So it's not really dependent upon one parameter, okay? It's dependent upon W over H, the ratio of the unstepped down height to the stepped down height, as well as the ratio of R over H, how big the fillet radius is, right? So when the fillet radius is smaller, we're going down here on the plot, the stress concentration factors get bigger. So you want to use a larger fillet to reduce the stresses, okay? So if we look at geometry with the following, right? So the radius is 1/8 of an inch. The unstepped down height is 2 inches, and the actual height is 1 inch. It steps down to 1 inch, right? In this particular case, W over H is 2, and R over H is 0.125. So if we look at W over H equal to 2, well, here's the curve for WH over 2. And it's this curve here. So sometimes you have to kind of interpolate between curves, but they're not too bad, right? So there it is, right? And now we want to find that curve where we get R over H equal to 1/8. So that's going to be, this is 0.15. So this is about 0.125. So we're going to take that up till it hits this curve here. So that puts me about there. And that's going to run me out to a stress concentration factor of about 2.05. Whoops. Wait, I don't know why I have 2.15. Did I look at, wait, am I doing this right? 0.125. This is 2.1. Yeah, this is really should be like 2.05. I kind of, this is more about. All right. And again, here they give you the equation for the average stress. It's just the force N over this area, right? The reduced step down area. So you can calculate that easily. That's how we've done it before. But then if you want to get the peak stress, you just have to multiply that by the stress concentration factor, right? I'll probably do the numbers here. I guess that's, that's what it is. So it's a very useful concept, right? It allows you to figure out these stress concentration factors, which can be really significant. Like in the previous example, you saw that we had the stress concentration factor of 2.2. In this case, it's 2.05. So we're actually doubling the stresses, right? So I should put a slide in here on this. I don't have one. But a classic example of this is like in World War I, the United States started to really exert its military dominance, or wanted to, and one of the things it started to do was build a navy, right? So they built these what they called Yankee ships, and they were riveted hulls. And what they found is when they took these ships out into the North Atlantic, they fractured in a massive way. They fractured as if it were like a toy boat and you just snapped it in half like it was invented. And the reason was because partly the steel, in the cold weather became brittle, but they never took into account the fact that they had all the rivet holes. So around each rivet hole, you had a significant stress concentration factor, kind of looking a lot like what is going on here. So they had cracks originate at the rivet holes. And if you've seen that, the rivet lines are, pretty lined up. So the crack just propagated across all the rivet holes and eventually fractured the ship right in half, which is why now you tend to see ships are not riveted. They're welded together, okay? Okay. All right, so here's an example for this problem, right? So here's a steel bar, and they give you the dimensions, and they give you an allowable stress, okay? So the stress cannot exceed 150 megapascals, all right? And they want you to find the maximum force P that you can apply where you won't exceed that allowable stress. Now, in this particular case, we have two stress concentration factor regions. We have a stress concentration factor here and a stress concentration factor here. Now, to look at it off the top of my head, I really don't know which one is going to be the limiting case, okay? And there's a lot of ways you actually can solve this, right? So we have to find P such that the stress at the hole and the stress at the fillet does not exceed our allowable stress. So we could use those calculations, right? And figure out that the stress max at the hole equals K times the stress average at the hole. But this is going to require P, and then we could figure out that the stress max at the fillet, which equals to a different K, I'll put an H here and an F here, because they're going to have different values. The average stress at that fillet, which again is going to be a function of P. So you could, this has to be less than or equal to the allowable, and this has to be less than or equal to the allowable. Right? So that could be one way we could choose to do this. All right. I'm going to do it a different way. And the reason I'm going to do this is just to show, this is related to what the approach we took in the method of assumed forces for the statically indeterminate problems. But I'm going to use this linearity concept to solve for this without having to like juggle variables, right? I'm going to just assume a force, and then I'm going to forward calculate what those peak stresses are, and I could see which one's going to be the greatest, and then I could scale it so that stress, where it exactly equals 150 megapascal, okay? So again, it's a nice way to solve these things, especially when you use tools like MathCAD or some other calculator, right? Like I said, this one's not too hard to just juggle the variables, but like I said, P shows up as an unknown here and here. And if you're not a big fan of doing that algebra, that algebraic manipulation, this is actually a pretty good way to do it because it's a linear problem, okay? So little different approach, but again, I think it's actually good to get used to this as well, okay? So we're going to do that, right? So that's what we're going to do. All right. So fine. So we've got P equal to 1 kilonewton, right? So P is equal to, we're going to assume it equal to 1 kilonewton. So first, let's look at the hole, okay? So at the hole, whoops, I didn't do numbers here. So at the hole, we need to get the diameter over W. So in this case, the diameter is 24 millimeters, and W is this distance here, that is 60 millimeters. Okay, so that is going to give me, whoops, let's see, that gives me 0.4. All right, so we're here at 0.4, okay? And if we go up to there, right, we get the stress concentration factor equal to 2.2, all right? So the average stress for our assumed case, right, is going to equal our assumed 1 kilonewton over this reduced area here, which is going to be the 60 millimeters minus the diameter, which is 24 millimeters, times the thickness, which is 20 millimeters, right? So that's going to be millimeters squared. And so that gives me an average stress of 1.399. It's a 3. I don't know why I disappeared. 1.39 megapascals, right? So that's actually going to be less than the 150. All right. But let's leave that for now. Okay. Well, actually, I didn't do the stress concentration factor. So the max, sorry, we forgot the max. So the maximum stress at the hole is going to be 1.39 megapascals times that stress concentration factor of 2.2. And that's going to give me a max stress of 3.06 megapascals. All right, so that's quite a bit less than the 150. If we were to double the force, we would double that stress. But to get to the 150, what would we need to do, right? I would need to get let's do it. So 150 divide, 150 divided by the 3.06 gives me 49, right? So in this case, 150 over the 3.06, that gives us a value of 49, okay? So that means the stresses can be 49 times higher, or in other words, the force could be 49 times higher. So that means if the force P equals 49 kilonewtons, at that point, that's going to give me a stress, a max stress at that hole of 150 megapascals. So exactly at the allowable limit. All right. All right. Well, let's check what's going on at the fillet. So now we're going to go to the fillet. So we've got the plot here to determine the stress concentration for the fillet. So we need to get R over H. So R over H in this particular case is 15 millimeters over H is the 30 millimeters. And so that is a half, right? So we're going to be right here, okay? And then we also have to get W on H. So W is 60 millimeters and H is 30 millimeters. So that's 2. So W on H is 2. And so that's this curve here. So that's going to put me right about there, a little above here. So that's about, it's 1.42 maybe. That's the stress concentration factor, something like that. All right, between 1.4 and 1.5, but pretty close to 1.4. And now we can get, again, we're assuming a force of 1 kilonewton, right? So now let's get the average stress. So the average stress, right, is the stress on that reduced area. So that's going to be the 1 kilonewton force over that area, which is the thickness of 20 millimeters times this reduced height of 30 millimeters, or 600 square millimeters. And that's going to give me a stress of 2.417 megapascals, okay? So actually, if you look at this, you can see that the stress you get at the fillet for 1 kilonewton is greater than the stress you get at the hole. So it's going to be this fillet stress is going to be the limiting factor. Right? So it's going to be the stress at that fillet hole that's going to be the problem. All right. Well, for 1 kilonewton, it's still less than the allowable 150. Well, wait, I didn't do the stress concentration. So the actual, so we got K is 1.42. So the max stress is 1.42 times the 2.42 megapascals. And that gives me a max stress of 2. Oh, I'm sorry, I did this wrong way. See, this is what happens when I do this. Sorry. If you do these numbers, you actually get this is 1.67, and that gives me the 2.42. Okay, so that's the peak stress. It's going to happen right here and right here. Okay. So there you go. 2.42 megapascals. Again, that's quite a bit less than the 150. So what would the actual force have to be? It's going to be 1 kilonewton times this factor of 150 over 2.42. Okay, so we need to increase the force by that ratio. That is actually 62 times, right? What's going on here? Did I do this wrong? Did it the wrong? Well, I got this the wrong way. Actually, the stress at the hole is the limiting factor. Yeah, this is, I'm sorry, this is I said this the wrong way. This is actually the limiting factor. And you can see that, right? Because the peak stress for 1 kilonewton at the hole is greater than the peak stress for 1 kilonewton at the fillet, right? So you could, I mean, you could still do this, and what you're going to find is that's to be, if you raise the force P by a factor of 62, right, you will get the stress at the fillet equal to 150 megapascals, right? So if P equals 62 kilonewtons, right, then this is going to give you a stress equal to 150 megapascals at the fillet, right? But again, you know, before you get to 62 kilonewtons, the stress at the hole will become greater than the allowable stress. So that's actually going to fail first. So in this particular case, the limiting design issue here is this hole. And so the maximum force that you can apply is actually the 49 kilonewtons, okay? So in this particular issue, like in this particular problem, it's really not that bad to put in for here P and then solve for P as it equals 150 megapascals. You know, we've done that several times, right? You know, you can do that, right? But the reason I did it this way was just to kind of show you how you can use linearity and sometimes superposition to save some of the like algebraic manipulation. Because I know sometimes students aren't the biggest fan of having the problems in terms of variables. They like to see numbers, right? So you can do that in a lot of problems by assuming a force, assuming it's a linear problem, seeing what the stress actually is, and then realizing that if you have to double the stress or half the stress, that means the force gets doubled or halved, okay? Because it's linear. All right. Is there any questions on that?
I do have a question, Professor. Yeah. For the, I got lost in the K. How do you know which, the fillet, what line do you have to pick for get the K?
Oh, it's okay, because these are, the different lines are different values of W over H, which is the W is this dimension over this dimension. So in this particular problem, W is 60 millimeters and H is 30 millimeters. So W over H has a value of 2. So you see, it's hard to see in here, but that is WH over 2, and it's showing you that it's actually that curve right there. Does that make sense?
Yes.
So that's the curve I want to look at. Now, where I'm going to look is where R over H is a half. So it's like kind of right there. You know what I mean? And I brought that over.
Yes, I got it. Thank you.
Yeah. Now, before I get into all the FEA stuff, let me just see. I wanted to show you. Oops. We'll go do an FEA example. But before I do that, let's just look at this a little bit. All right, so I'm going to post these PDFs, right? So these are tables from a pretty classic book called Rourke's Formulas for Stress and Strain. That's down here on the bottom. I actually have the 7th edition. It's It's probably like the 20th edition now. These things have not changed over, 30 years since I was in college, right? But here they are, right? So what they do is, these tables to allow you to calculate stress concentration factors for a variety of conditions. So in this particular case, we have a bar with two symmetric stepped notches. We can have the same thing in bending. We can have stress concentration factors for a bar with V notches, one for a single notch, one for a single V notch, axial bending, all sorts of different types of geometrical situations, right? Here's a plate in biaxial stress with a hole in it, right? So, I'm going to not go through all these, but, here ones are ones that are in torsion, right? And I think there's probably one that's similar to the ones that they show in the book. Maybe? I don't know. Maybe not. They're probably in there, but I probably omitted them. Okay. Well, here you go, right? Here's the square shoulder with the fillet, okay? Now, in this particular case, they don't give you a plot. They actually give you an equation, all right? And so, like actually these days, I think the equation is preferential to the plots because plots are kind of, it's a manual thing. Like once you type in the equation into a calculator or into MathCAD or MATLAB or something like that, you can solve this over and over again. And here you can see the parameter is in terms of 2h over d, right? And in this particular case, h over d, that's another way of getting at this w over L. It's a little bit different than what was in the plots. And then these coefficients C depend upon h over r. So the step down over the radius. So again, you could figure out those values, get C1, C2, C3, C4, plug it into here, put in the values of H and D, and get your stress concentration factor. And you get the same thing that you would see in the plots, right? It's just a different way of looking at it. Typically, when you look these things up, they're given more in this equation format than in the plot format, but sometimes you'll see the plot formats, okay? So for all the problems you have to do in this class, I'm only gonna give you ones that are in the book. So I won't give you like, 2 notches, right? But they do exist. And like I said, I will post, I'll post these slides. Well, the slides are already up there, right? So all those factors are there, okay? And actually, if you do have some funds available, I know that's probably not the case for students, right? But this book here is a really good reference book. So you can purchase it, or if you are creative and search for the PDF, you'll probably find it on Scribd or something like that, okay? All right. All right. Okay, so just for the heck of it, I did the same problem just to sort of show what's going on, but I solved it in Fusion 360 using the finite element solver in there, okay? So I just went in and I made a solid model of the same dimensions, okay? And, I already solved it, but so I put a force on here of 49.1 kilonewtons. But, again, the reason why I wanted to show it using the assumed force is because if you're doing a finite element simulation, right? And you want to find out what's the maximum force that you can apply before the stress exceeds an allowable stress, you may be tempted to just keep rerunning the finite element simulation at different force values until it matches that allowable stress. You could do that, but that actually would be a big waste of time. And the reason is the same reason that I was able to get away here with, oh, I erased it all, solving these problems by assuming the force equal to 1 kilonewton, seeing the stresses that arise, then figuring out how those peak stresses scale to the allowable stress and using that to scale the force. So even though for a hand calculation, you can do the algebra and solve explicitly in terms of the force P, you cannot do that in a finite element simulation. So if you wanted to solve something like this using finite elements, really your best bet is to assume this force, right? See what stresses you get, and then figure out what's the margin, what's the factor of safety between the peak stress that you find in the finite element simulation and your allowable stress. If it's 49.1, then you know your load has to be 49.1 times the load that you apply. So actually, I think I did do that in the finite element too, just to check, but you know, so I cheated here a little bit and I put directly the 49.1 on here, okay? And when you do the simulation, right, you get the following plot for the stresses. So these are the normal stresses in the x direction. And here you can see the stress concentration factors at the holes, as well as a little harder to see, but the stress concentration factors at the fillet. The peak stress is right here, and it is pretty close to that 151 megapascals, right? We wanted the stress to be 150, so a little bit over, but that's, you know, just from numerical modeling errors, okay? All right. So it works out quite well. The stress concentration factor really does do a good job. Like this is, you know, 1% error, 2% error, which is pretty good for a finite element simulation or a hand calculation, right? So, okay, so here I just did all this stuff. So, okay, so how did I want to set this up in Fusion? So let me just talk a little bit about boundary conditions. Since you've already run these a little bit, you know, when we do finite element models, this idea of picking the boundary conditions really is a big deal, okay? You have to fix every component, so you can't just put a force on the right and left side. It won't allow you to solve that. So what we're going to do is put the force on the right side and then not fix fully the left side, but put it on rollers so it's free to contract in the lateral directions, because now you know that there's a Poisson effect, and as this starts to elongate, right, due to this force, it's going to want to contract down in the out of plane, you know, in the transverse directions, both in the vertical direction here and then in and out of the board. So if you actually fix that end, you would see, you know, a deformation that would look like this at that point. You know what I mean? I'm exaggerating, right? And this would be incorrect. What we really want to see is this, you know, kind of neck down like that, right? Which is actually what we see up here in my results. You can see it looks pretty good. All right. So how did we do that? Okay. Well, on this right side here, we pick this face and I put a uniform distributed force on it. So I pick the face, put the force in the normal direction, and I assign the magnitude of 4.91 kilonewtons. I'm sorry, 49.1 kilonewtons, or 4.91 to the fourth newtons. And then on the left side, which is a little harder to see, if you look at the end, this is looking down at that surface here. Oops, get rid of this nonsense. We didn't fix it okay? But what we did was I picked this face and I fixed it in the X direction. Oh, I'm sorry, this is shown this way. So this is the Z direction, and this is the Y direction, okay? So I'm gonna fix this face in the Z direction. So you can see I selected just the Z component, so it's fixed only in Z. Now, it can still move up and down and in and out of the page. So I wanted to just fix one point. So I just grabbed this one little corner, and I'm going to fully fix that in X, Y, and Z. So just that one point, it's like it's pinned, right? But if I fix the entire face so it can't move in Z, and then I fix just a single point fully in X, Y, and Z, that is going to approximate it like it's on rollers. So if you think about it, right, if we picked like all the faces and fixed them in X, Y, and Z, that face would not be allowed to contract laterally due to the Poisson effect, and you would get stresses arising from that fixed constraint, right? So in reality, we want to put it like on rollers. So that's what allows you to do that. Another way you can do it, and I didn't do it here, but you can also look at the fact that this is symmetric, and you can put this symmetry plane on rollers. Now, I didn't do that in this particular case because I wanted to show clearly the stresses, concentrations at that hole. So I chose not to do that. But actually, I probably would have done that if it wasn't for this class, okay? So those would be appropriate types of boundary conditions. And if you run those, you know, there's the mesh. So I made a mesh that looks roughly like this. I tried to make sure I get some small elements at the fillet and the hole because I know I'm going to see some peak stresses there. And, you know, here's what you get. So like I said, we do quite well at getting the peak stress. And not only that, we actually do quite well here. I get the max stress here to be 1.22 megapascals when, in fact, what I should have got was 49 times 2.4. So what I would have expected here from the hand calculation is a sigma max equal to 118 megapascals. So again, not too bad, right? So I have about a 1% error at the hole and a 3% error at the fillet, okay? Now, honestly...
Professor, I have a
Yeah.
question. How do you calculate those errors? How did you get those errors?
Oh, okay, this is the error between my hand calculation, which I'm going to say is correct, and my finite element result, which I'm going to say has an error associated with it, okay? So 151.7, that's the error with 150 oops. Right, for my hand calculation, the stress I get at the hole is 150 megapascals. What I get in my finite element simulation is 151.7 megapascals. So that gives me an error of 1.1%. Now here, from the hand calculation, I would expect to get a stress, the fillet, of 118 megapascals. But in my finite element result, I actually get 122 or 123 megapascals. And that gives me an error of 3%, okay? So a little bit more. Very likely, if I had used smaller elements, that error might go down, okay? All right? There's a little bit of an error in the assumptions too with the stress concentration factors, but those are actually quite good usually, you know? I wouldn't get too hung up about, you know, which one's right and which one's wrong, but the real point I wanted to make is that, you know, in general, for an engineering hand calculation, you know, typically, if you can get a result within 15%, very likely 25%, you're doing real good. That's really good because the assumptions are really crude for hand calculations. In this particular case, we do pretty well because the hand calculation is basically exactly what's going on geometrically here, right? There's nothing else weird going on, right? There's no other assumptions that went on into there. Okay. For the FEA calculations, 5% is real good. It's real good. So, that's why we have factors of safety. That's why we designed the factors of safety. And a lot of times in problems, the uncertainty in the loads, the geometries, the material properties, whether it's the allowable stress or the, Young's modulus and stuff, is such that, even if we can get a numerical error of 5%, those unknowns make the error actually even higher, right? So I guess what I'm trying to point to is that, you can do some of these very academic problems and get a good result, but practically, you're going to be limited in those, all right? All right. And I think that's all I wanted to do, okay? So I'm gonna probably assign this or something similar to this as the next finite element project, and you'll actually also be able to compare those to a hand calculation in the book and basically go through the same exercise yourself. Okay. All right. Any questions on that? All right. Very good. Well, have a good rest of the day.